Okay, so let's begin. आज हम जो है वो दो टॉपिक्स मेनली स्टडी करेंगे. Postulate 4, which is on quantum measurements. इसमें हम देखेंगे generalized measurements, projective measurements, and POVM measurements. And then we will also discuss the last postulate, postulate 5, which deals with the composite systems. Okay, so before I begin, let me ask Munib to summarize the three postulates that we have already studied. Good. So number one, we have a Hilbert space where our physical system lives, a closed physical system, and its state is array. Good. Number two. Observables are Hermitian operators. Good. Good. So the third was all evolutions are unitary. Okay. The evolutions in time and space, they are both unitary. But all of these postulates we are studying for closed quantum systems. From the next lecture on, we will start discussing open system, and we will see that a quantum system, which is a subsystem of a larger quantum system, may not necessarily, follow any of these axioms. It still does follow some conditions, but they are more general than these 5 postulates. So today, let's discuss the measurement postulate, which is one of the most controversial in terms of its interpretation. Measurement. So I'm going to define this postulate in a general sense. And the reason is this, कि जो quantum information है, उसमें usually we need to work with generalized measurements than with the simple projective measurements, जिसमें कि normally जो experiments इनमें हम energies या positions से deal कर रहे होते हैं, जैसे chemistry या condensed matter physics में we are mostly talking about projective measurements. But here we will need more general measurements, and hopefully today in a couple of examples you will also see that why do we really need to have a more general measurement set than just the projective measurements that we are used to. And then जब generalized measurement postulate में describe करूंगा, then I'll describe two special cases which are the most common one, the projective measurements and the POVM measurements. And then hopefully today we'll be able to end the discussion on the postulates by discussing the composite system as well. So the general measurement postulate, or you can say the fourth law of quantum physics, is that measurements are described. You can find, more verbose statements in the book. Here, I'll just give a summary. By a collection of measurement operators, let's call them M sub M, with this index M refers to the possible measurement states. And then this is an operator which gives us the probability of finding our system in that state. So this is a set of operators. These are measurement operators. And this measurement, this set has to, follow only one general requirement, and that is that the set is complete, which means that uh, any state, any possible state of the system can be described as the state where your measurement operator takes you, all possible states where the measurement system takes you. For example, you have a state that describes the polarization of a photon, okay, in a plane. So light might be coming towards you and you don't know what the state is, and you want to prepare a set of measurement operators. So one possibility is this, that you say, okay, one measurement state is this and the other measurement state is this, because any general state you can describe it as a linear superposition of these two, right? But you can also take this and these two states as your measurement states as well. They're not orthogonal, but still you can represent any other state in this plane as a superposition of these two states. So the only thing that in general this measurement operator has, the set of operators have to satisfy, is this completeness relation in general. And then we say that the probability of finding your system in one of the index state M is given by the norm of the norm square of your measurement operator operating on the state size. So this is the state that we are trying to measure. So when I apply an operator on this, I get some state. So its norm square is the probability of finding my system in this state indexed by M. So this is part of the postulate. And since the probabilities of all of the options have to be, add to 1, so that which comes actually from your completeness relation, which means that sum over all possible states should give you 1. This is actually equivalent to this statement. You can just take a psi state from left and right over here, and you can check that 1 should be equal to psi dagger psi. So this is equivalent to the completeness relation. So this is the generalized measurements. And let me now discuss two special cases. The first is what we call projective measurements. By the way, there's one thing that is still here, and that is that the state after the measurement the state of the system is given by the normalized state this. So you can divide it by its norm to normalize it. So it's like this: before measurement, you have psi. Before measurement, and after measurement, you have this state, psi, and you can normalize it by dividing its norm. All right. So let's define special cases. So any set of operators that satisfy this requirement is a measurement operator, that it's complete. Okay, this is important. In general, that is all that you need. That's a special case. So far, we didn't say anything about hermeticity. यानी m dagger m तो अगर आपके पास एक ही पॉसिबिलिटी है तो फिर ये ठीक है, अदरवाइज द सम of this is identity. हम एक दो एग्जांपल लेते हैं, then you will actually be more sure. ये जो जनरल स्टेटमेंट है इसका आपको थोड़ा ज्यादा अंदाजा होगा. लेट मी गिव सम स्पेशल केसेस, फिर आपको जनरल की भी जो अंडरस्टैंडिंग है वो बढ़ेगी. सो इन द स्पेशल केसेस, द फर्स्ट स्पेशल केस दैट वी टॉक अबाउट इज व्हाट वी कॉल प्रोजेक्टिव मेजरमेंट्स. और इनका एक दूसरा नाम है वॉन न्यूमैन मेजरमेंट. उसकी वजह ये है कि ये बोला हेलो, इसकी बैटरी लो है. यार ये क्लासरूम स्टाफ का पता है. चले आपके पास ये बैटरी चेंज करने वाली. ये लोग क्लासरूम करवा के तो अपने काम करने भाग जाते हैं. चले सीएफ अगर ये दोबारा बंद होता है ना तो देखेंगे कि हम खुद से कर सकते हैं चेंज. ऑलराइट, सो अली सादन भी आ गए. वेलकम अली. आपने जो मीठी पार्ट है वो मिस कर दिया. एनीवे, सो लेट्स नाउ डिस्कस दिस प्रोजेक्टिव मेजरमेंट. अगर इन एडिशन टू, अच्छा इसका नाम वन न्यूमैन इसलिए है कि दिस पर्सन put this thing for the first time, these measurements, in this mathematical form. So that's why they are also called von Neumann measurements. In addition to this completeness, if your operator satisfy two additional requirements. Number one, they are orthogonal. And number two, they are Hermitian. Then we call these measurements projective or von Neumann measurements. Okay, and let me show what we mean. We mean that first of all, this thing mean that mm dagger is mm, and this, sorry, ये जो है ना ये है, और जो orthogonality है, this means this thing, that mm dagger is delta m prime mm. So if the index is different, the product is 0. If the index is same, then, so इसको आप यूं लिख लें. So if the index is same, which means that mm square is mm. If the index is different, this means that this is 0. All right. So when we have these two additional things, then we call these measurements projective measurements. ठीक है? और most people talk about जो language इसके लिए invent जो ज़्यादा use होती है वो ये होती है कि suppose you have a system in some state psi. Let's say you're talking about spin of a system. So the two possible measurement states after measurements can be, let's say, spin up or spin down. So you can define one measurement operator, M1, that gives you spin up, the other measurement operator that gives you spin down. And let's say your state, incoming state that you want to measure is some psi which is superposition of this thing. So there is some probability of getting up and some probability getting down. And the most common language that is employed is this, okay, you have a state with some probability, both states. And then when you do measurement, your wave function collapses to one of the, state that is given by the operator. Agarche, there is an equivalent and perhaps slightly better language जो आप इस तरह से भी कह सकते हैं कि चूंकि because some people have objections to this collapse thing, and that is that कि equivalent description ये हो सकती है कि suppose before measurement your state is something like this, and then once you do measurement, then you know what the state of the system is. So now your probabilities have changed. जो पहले lecture में you remember when we were talking about base, कि जो probabilities हैं they depend on your knowledge. So before measurement, we didn't know what the state of the system, was in terms of those two possibilities. So we assigned some probability to both. But after measurement, we know that the system is in this particular state. And then when we give it state, we might give it, something like this, that, okay, since we know that it's in this particular state, its wave function would be this. So we modify our probabilities based on our previous knowledge. So that is sort of an equivalent description. अच्छा, ये जो projective measurements हैं, usually जो symbol है, you can actually now use this thing. So I will use this symbol PM for MM when my MM is Hermitian and MM is orthogonal. Okay, so this I will use to represent general, and this I will use to represent the projector measurements. So this projector has special properties, which is number one, that the square is equal to itself. We can check from there, and also that we can see one additional thing, कि जो ये relation है, this now transforms to this, that my set of projectors is a complete set. And since there are, it is no Hermitian by definition of projective measurement, it means that I now have a nice description. Let's say you have some observable M. Okay, this is my observable. You can think about this could represent energy. Okay, energy observable hai, momentum, position, or any other property of the system, angular momentum, etc., etc. So since this is a Hermitian operator, by postulate number 2, I can expand it in terms of my projector operators. And now I choose each of this PM as my measurement operator. And when I do measurement, I'm essentially measuring different possible states corresponding to this observable. So this is the observable, and these are the measurement operators. अगर आप थोड़ा सा concrete view लेना चाहते हैं, तो you can think about like this. क्योंकि M Hermitian है, तो हमने पहले से देखा है कि we can do a spectral decomposition of Hermitian operators like this, right? ठीक है, और आप इसको बेशक यूं imagine कर लें कि each of this is actually a projector. So each one of them, and actually we can even have a linear combination. जरूरी नहीं कि आप एक एक को ही लें, कि जो एक इंडिविजुअल एलिमेंट है इस सीरीज का, उसको आप एज ए प्रोजेक्टर लें, उनका लीनियर कॉम्बिनेशन भी एक प्रोजेक्टर हो सकता है. बहरहाल, इफ यू टेक देम टू बी इंडिविजुअली, देन you can correspond each one of them to this Hermitian projector operator, and then this eigenvalue is just this M. Okay, let me give you some description. फर्ज करें कि हम एनर्जी की बात कर रहे हैं, so हैमिल्टोनियन की बात कर रहे हैं. So you can express this Hamiltonian in energy eigenstates like this. So फर्ज करें, so N1, 2, ये आपका जो सिस्टम है उसका एनर्जी स्पेक्ट्रम है. So then I can have one measurement operator P1 as corresponding to the ground state, the second measurement operator corresponding to the first excited state, and so on. and I have some physical, operators that when I get some state, it can give, it can perform these measurements and tell me which, energy state my system is. So आप यहाँ से देख लें कि ये सारे orthogonal हैं because all of these energy states are orthogonal, और ये सारे Hermitian हैं. So essentially अगर आप इस और इन सब को अगर आप sum करें with these eigen values, you can get the Hermitian operator itself. So this is my observable, and these are the measurement operators corresponding to this observable, and this, complete set would be the set of measurement operators corresponding to this thing. All right, so let's see how we can get the average value of an observable. So I want to find the expectation or average value of an observable. So this, by definition, is the sum of all possible values multiplied by with their probabilities. Okay, so this is the statistical definition of average of a quantity. जो भी numbers हैं, उन number की जो probability है उनसे multiply करके सब numbers पे add कर लें, you get the expectation value. Now here, if we put the expression for this, PM क्या है अब हमारा? PM is whatever the state, and then this is PM psi, and I can write it like this. And this is nothing but the decomposition of the Hermitian operator. So that's why the expectation values of observables can be written like this, because we are assuming that we can write this Hermitian operator as a linear combination of projectors, and then each projector can give us the eigenvalue corresponding to that state, and then we can add it up like this. All right, so the state after measurement is by the first postulate, by the generalized postulate. What's this? PM psi is the state, और ये इसको normalize करने के लिए है, ठीक है? So this is the state right after the measurement. So let's say you have some state psi incoming to your measurement operators, and we are not discussing the measurement operators, okay? That's a discussion, which is very intricate, and there's no consensus, I would say, formalism for this. And it's complicated simply because this measurement thing is done by your operators. फर्ज करें आप एक molecule ही है, उसकी वो energy spectrum measure करना चाहते हैं. You have the whole thing around it. You might put those molecules in a tube, किसी चीज से उसको आप shine करते हैं laser light से, then you have all the operators around it to find its, some optical Raman absorption or some type of spectrum, और उससे आप वो find करते हैं. So it's a very complicated and a very hugely complicated quantum system. और अगर आप उसको classically model करते हैं, so this essentially, ये जो description, ये जो postulate 4 है, इसका होने की वजह ही यही है कि जो measurement system है, अगर हम इसको जो पहले postulates हैं उनकी मदद से describe करना चाहें, तो it's a hopeless task. क्यों? क्योंकि देखें, पूरी यूनिवर्स क्वांटम सिस्टम है, आपकी लैब भी क्वांटम सिस्टम है, जो जिस क्वांटम सिस्टम का मेजरमेंट करें वो भी क्वांटम सिस्टम है. सो ऑल ऑफ दिस इज अ क्वांटम सिस्टम. सो व्हाट यू कैन डू, अब मेजरमेंट को इन प्रिंसिपल इस तरह भी कर सकते हैं ना, कि यू लेट्स से हैव एन आइसोलेटेड सिस्टम, एंड व्हेन यू वांट टू डू मेजरमेंट, you might have some a window that you open up, and then your system couples with the quantum system of the lab or measuring operators, and then it all together evolves under the unitary operator, and then after a while you switch off this interaction, and then that's how the measurement is performed. लेकिन जो आपका lab system है, ये बहुत complicated quantum system है, and at least with the capabilities that we currently have, we can neither theoretically or computationally, we can't work out what would happen to the total system under this unitary evolution. So इसीलिए इसकी जगह पे we have this measurement postulate that we say, okay, somehow we are able to do measurement, but once we do this measurement, we get our system in some form. This को you can normalize it like this. So this is what we get. So for projective, I'm calling it P. So let me put it P. अच्छा, अब इसका मतलब ये है कि once you have your system in this one of the eigenstate, then if you do the same set of measurements, okay, so this is some observable. If you pass it through the same measuring operators, which again measures in the same eigenbasis जिसमें आपने पहले किया है, immediately after the first measurement, you will get the system again in the same state with the probability 1. And you can do the measurement again and again. You will find the system in the same state with probability 1 if you repeat measurement, soon enough. You don't let it evolve unitarily for a while. Okay. Any questions? Let me take another a quick example. First, Karim, you have a state psi, which is the plus state. And just to remind you, the plus state is this state of a two-level system, a qubit. And then we want to find the measurement probabilities for observable Z. Okay, Z is some Hermitian observer. कोई भी Hermitian operator जो है, you can have it observable. जी? कि अगर आप वही जो मेजरमेंट है वो दोबारा से उसी सिस्टम पे अप्लाई करें,